Welcome to my channel V Concepts CHM. This is the fourth part of the series of Introduction to Lasers, where we are going to see the construction and working of helium-neon laser and ruby laser. Helium-neon laser. This is the first gas laser which was invented in 1961 by A. Javin, W. Bennett and D. Heriot at the Bell Telephone Laboratory in USA. Construction. It consists of a long discharge tube whose diameter is about 1.5 centimeter and 80 centimeter long. There are two electrodes inside the tube. These electrodes are connected to a high voltage power supply. The active material for lasing action is a mixture of helium and neon in the ratio of about 10:1. The partial pressure of helium is about 2 to 10 times higher than that of the pressure of neon. This condition is later on useful as it reduces the probability of a reverse transfer of energy from neon to helium. The tube is sealed by inclined windows arranged at its ends. Two mirrors are arranged externally. M1, which is a perfectly reflecting mirror on one end, and on the other end the mirror M2 is a partially reflecting mirror. So this complete system forms a resonator system. Now we will see the working. As the power switches on, a high voltage is applied across the gas mixture. This high voltage produces energetic electrons that travel through the gas mixture. Hence, the electrons are accelerated between the anode and the cathode through the gas mixture. So, because of the energetic electrons, the helium atoms get excited and the lower state electrons of the helium, they gain enough energy and they jump into the excited states or the metastable states. So this is the excited state, this is the metastable state. Metastable state are the excited states which have relatively long lifetime. That is, the electrons can stay in this state for a longer time compared to the electrons in the excited state. We can call a metastable state as a temporary state or an intermediate state where the atoms can stay a bit longer. The metastable state electrons of the helium atoms can return to the ground state by transferring energy to the lower energy state of the electrons of neon atoms through collisions. So here the helium atoms, they are returning back to the ground state. Before they return back to the ground state, they transfer the energy to the neon atoms. So here it is shown in this diagram that the helium atoms, they have come down to the ground state after transferring energy to the neon atoms. So when millions of electrons of neon are excited to the metastable states, we would achieve population inversion state. So now the electrons of the neon atom has gained energy from the helium atoms, and now they can go to the metastable states, so that we will reach the state of population inversion. So the atoms, we will find that the number of atoms in the metastable is more than that compared to the ground state. So after this state, the electrons of the neon atoms will fall into the next state with lower energy, which is called spontaneous emission. So that is shown in this diagram. And in this process, the photons are emitted. These photons, they oscillate back and forth between the two mirrors, which we are seen in the construction part. The two mirrors M1 and M2, between these two mirrors, the photons will be oscillating back and forth because of reflection, because they suffer multiple reflection. And this will continue until the photons will stimulate the other excited electrons of the neon atoms and cause them to emit light. So that will be the process of stimulated emission. That is, these photons which are produced due to spontaneous emission will later on lead to the stimulated emission of the excited electrons of the neon atoms, and then they will cause them to emit light. And that way, like one photon will give rise to two photons will multiply to four photons will multiply to 8, and that way optical gain is achieved. Applications of the helium neon laser. It is widely used in the laboratories as a monochromatic source. It's used in laser printing, in barcode reading. Next is the ruby laser. It is a solid state laser. It is a 3-level laser designed by T.H. Maiman in 1960. It is also called as doped insulator laser. So ruby is aluminum oxide with a small percentage of chromium atoms replacing some of the aluminum atoms. So compared to the aluminum atoms, the concentration of chromium ions is very less. Construction. There is a cylindrical ruby rod 4 cm long and 0.5 cm in diameter. The two ends of the rod are made perfectly flat and parallel to each other. One end is completely silvered while the other is silvered partially. Hence, this crystal itself acts as a resonant cavity. The rod is surrounded by a helical glass tube and this glass tube has a flash lamp with xenon gas. The flash lamp, when it is activated with the help of the power supply, will produce flashes of white light. So we'll see the working. Now, when the light energy is supplied by the flash lamp to the laser medium, that is ruby. So, light energy is supplied to ruby with the help of the flash lamp. The electrons in the lower energy state even gains enough energy, and they will now jump into the excited state, which we denote as E3. The excited electrons in the state E3, as it is excited state, the electrons cannot stay there for a longer period of time, and hence they will come back to the metastable state E2 within a time of 10 raised to minus 8 seconds. And there they can stay for a longer time, for about 3 into 10 raised to minus 3 seconds, which is much greater than the lifetime of the state E3. So as a result of this, the number of electrons in the metastable state E2 will increase. That is, if you compare it with the ground state, there are more number of electrons in the metastable state, and hence we have achieved the population inversion state. Now, since the population inversion state is not a stable one, it is a non-equilibrium state, the one or the two electrons will come down to the ground state spontaneously, so that the process of spontaneous emission will take place, and in the process of spontaneous emission, photon is emitted. So a chance photon is emitted by the chromium ion. It will later on initiate stimulated emission in the other chromium ions in the metastable state. So suppose this photon will then later on stimulate the ions, the chromium ions present in the metastable state. And so the process of stimulated emission will take place, which will again lead to the emission of photons. So this photon will travel through the ruby rod in a direction parallel to the axis of the rod and reflect back and forth by the reflecting ends of the optical resonator until again it stimulates an excited chromium ion. So continuously multiple reflection of the photons will occur, and these photons will stimulate the other excited chromium ions, and that way the more photons are emitted. So the photons that are emitted by the stimulated excited chromium ion, they are exactly in the same phase with the stimulating photon. So all the photons will be in the same phase. The stimulated transition of the chromium ion from the metastable state E2 to the ground state E1 is known as laser transition. So these photons, they are all in phase. They will stimulate more chromium ions, and hence the number of photons emitted increases. This process repeats, and hence the in phase photons get multiplied, and hence what we will get is a strong and coherent laser beam coming out from the partial reflecting surface. Thank you for watching this video.